Salim. Well done. So now salts. We said we describe the substances we use. We classify them into three. What's it? The substances we use: acid, bases, and salts. Exactly. Now, you see, the salts are the ones we want to talk about now. But let's quickly do a recap of what we've learned about acid. Now, there are acids and bases primarily, we take them together. So, there are three schools of thought, right? Historically speaking, in the historical development of the definition of acid, there are three scientists that we make mention of. The first guy is what? Svante Arrhenius. And what was his postulate? What was his idea of an acid? He said that an acid is a substance that does what? Produces hydrogen ion or hydronium ion as the only positive ion when dissolved in water. Have you forgotten this thing already? As a substance that produces hydrogen ion or hydronium ion. This one is how you call it hydronium or hydroxonium ion. Exactly. So when dissolved in water, so if you see a reaction like this shows that this thing is reacting with an acid because this will give us hydronium. Does this make sense? So this proton comes from an acid either of HCl, H2SO4, HNO3. These are the commonly used acids. Is that clear? Or basically, when we're referring to strong acids, these are the ones we are talking about. Is that clear? HBr, like the families of this one. But these are the most common ones. Now, but the rest, like H3PO4, H2SO3, H2CO3, these guys are weak acids. Okay, then other ones are now organic acids. So these are weak acids. But the point is this, that Arrhenius was saying that if you dissolve this guy in water, they will produce hydrogen ion as the only positive ion. Is that clear? That was the first and primitive idea of an acid. Then the same guy said that a base is a substance that produces Arrhenius' base now. This is Arrhenius acid. Arrhenius base is now a substance that produces hydroxide ion. Exactly. This thing means concentration, though. This box that I put it. Exactly. So it says a base is a substance that will produce hydroxide ion as the only as the negative ion when dissolved in water. It will produce hydroxonium ion as the negative ion when dissolved in water. Now, actually, you can already see there when we ionize water. When we ionize water, we'll talk about ionic theory. It was one that postulated in ionic theory, right? Arrhenius postulated in ionic theory. What is an ion? There's one between an atom and an ion, like you have said. An atom is basically any small part of an element. Thank you. But an ion is that atom when it has become charged. Exactly. And there are two types of the ion. You mentioned cations and anions. Cations are metals that have become charged. So cations are those guys that normally lose electron. They normally do what? Lose electron. Anions are those guys that normally gain electron. Do you understand now? When we discuss metals and non-metals again, we are going to discuss it in full. We'll be able to come on Monday here. So I would have taken permission to use this place so that we can have a longer session. Exactly. So they lose electron, these guys gain electron. So they become ionized. So metals become ionized by the losing of electron. So the kind of ion they become is called a cation. Non-metals become ionized by gaining electron, and the kind of ion they become is what? Anion. Example of cation: Na plus, Ca 2 plus, Mg 2 plus, Al 3 plus. So these guys are cations. But look at chlorine, for example: Cl minus, O2 minus, OH minus, PO4 3 minus. All these guys are anions. Exactly. Notice they are formed by non-metals. Make sense? Is it making sense? So ionic theory is saying that when substances dissolve in water, they will dissociate into freely moving charged particles called ions. Exactly. So that's why we need to ionize. Okay, so Arrhenius was not that brought about the idea of ionization. So he said that a base is a substance that if you dissolve it in water, for example, NaOH, for example, NaOH, if this guy dissolves in water, it produces Na plus OH minus. So this is a base. Why? Because it's producing what? Hydroxide ion. Exactly. Now, what about water? If you ionize water, you're going to have H plus and OH minus. Is it making sense? So you can already see that when you ionize water, you are going to get a proton. And again, guess what? Hydroxide, right? So it means that water has both properties of an acid and a base. Hence, we call it is what? Amphiprotic. We say it's what? Amphiprotic. Water is an amphiprotic solvent. Exactly. A substance that produces behaves like both an acid and a base. We also call it amphoteric. We also call it what? Amphoteric. The reason why we call it amphiprotic in the sense that it can donate a proton or collect a proton. Make sense? You know, in this case here, it's collecting a proton, right? Do you notice that water collected this proton from either of these acids? Is it making sense? So, but here, excuse me. I didn't give any reaction for base. Okay. Here it behaved like a base, right? But look at this reaction. Let me show you a reaction like this: H2O plus NH3. Before we use this reaction, let's go to the second definition. The second idea, yes, sir. The second idea of an acid is according to Bronsted-Lowry. So Bronsted-Lowry acid is a proton donor. Bronsted-Lowry, they define acid as what? Proton donor. Don't forget to, I've told you how to remember, right? Bronsted. Didn't I tell you how to remember? Bronsted, proton donor. Exactly. Then the last one is Lewis. When we're doing Lewis structure, do you remember Lewis structure? Do you remember Lewis structure? Do you know how to draw Lewis structure? Yes, sir. I hope we can still draw Lewis structure. When we start organic chemistry, I won't go back to it all. Okay? So, Lewis structure. So, Lewis acid is an electron pair acceptor. You see, it's the opposite. This one said acid is a proton donor. If it's donating proton, what is it accepting? Electron. Is it making sense? Let me show you. So here, for example, an acid is donating a proton to water. Make sense? And a base, so water is acting as a base here, right? Is it making sense? Yeah. An acid is a proton donor, according to Bronsted-Lowry, but a base is an electron pair. An acid is a proton donor, right? And what will a base be? Proton acceptor. Good. Is it clear? Proton acceptor. That's a base. Acid, proton donor. So this guy is an acid. It donates proton to water, right? I want you to see the amphiproticity of water. Its ability to act as a base and an acid. You see here is accepting an acid. Is accepting a proton from this guy, right? So water is reacting as what here? As a base. God bless you. Because the proton acceptor here. But as a base is a proton acceptor. So here, so it's acting as a base, yeah, sorry. But water can also act as an acid. Okay, so let me show you where it's acting as an acid. Here, this guy will form NH4 plus OH minus. What do you notice here? Who is the acceptor of the electron here? Of the proton here. Do you notice that it was this guy that accepted the proton? Exactly. You know the idea of Bronsted-Lowry that gave us that brought us the concept of conjugacy. So we have this one being, this is our acid, this is our base, this is our conjugate. This is our conjugate what? Conjugate what? Conjugate base or conjugate acid? This is our conjugate acid. Let me show you something. What's an acid? You have to remember. See, acid is the guy that is always donating the proton, right? Just listen first. Just listen first. You'll get it. It's very simple. So that you will never forget again. Listen. Acid. We said this as our acid. We want to look at acid behaving, water behaving like an acid. We have seen water behaving like a base here, right? Here, what did water do here? Water broke up into H plus and OH minus here and gave this guy a proton, became this. Make sense? Now, here, water is a proton donor, right? So water is our acid. Is that clear? So this guy now is our conjugate acid. Why? Because if we want to reverse the reaction, what will this guy do? It will give back the proton to this guy, right? So since it's the one that will give proton now, to be the what? Acid. You see now making this now? So you don't forget again. This guy is the conjugate acid because it's the one that will return the proton to this guy. Is it making sense? So this guy will accept so being the conjugate base. But don't forget, what I'm trying to show you is that is the amphiphoticity of water, here acting as an acid. Here, we in the presence of a strong acid. Just now, that's another way to think of it. When acid sees its boss, when water sees its boss in acid, what will it act as? The base, God bless you. But when he sees his boss as the base, what will he act as? As an acid. Do you understand now? Because this base is stronger than water. Then this acid is stronger than water as an acid. Is that clear? Alright. So then the last idea is the Lewis idea, electron pair acceptor. Now that idea is not of consequence to what we want to discuss. So we'll just go to salt. Now, what is a salt? Right, salt. A salt is a substance. A salt is a substance that is produced. A salt is an ionic compound. Not as a substance. A salt is an ionic compound. I want you to understand the idea. A salt is an ionic compound produced when the replaceable hydrogen ions in an acid have been replaced. When the replaceable hydrogen ions in an acid has been replaced partially or completely, when the replaceable hydrogen ion in an acid has been replaced partially or completely, take this by here. That thing will soil your book. You don't use pen on this kind of paper. Do you understand? Has been replaced by a metal, has been replaced partially or completely by a metal. Is it clear? Has been replaced partially or completely by a metal. Now, so from that definition, in fact, you should already know one of the easiest methods of preparing an acid. Basically, the action of a metal on an acid, of preparing a salt. The action of a metal on an acid. Just now, because we said it's an ionic compound that is formed when all the replaceable hydrogen ions of an acid have been replaced by a metal, partially or completely, by a metal or ammonium ion. It's not only metals. So it is both metals and ammonium ions that can replace it. Ammonium ion. Don't forget, both metal and ammonium ion replace the hydrogen to form salt. Now, what that is saying is this. Look at this acid, HNO3, for example. So if I want to replace this, you know this HNO3, if I ionize it, what will it form? H plus NO3 minus. Now, now, if I basically just replace this by if I replace this by sodium, what will it give me? NaNO3. Is that clear? It has replaced this guy. Does it make sense? If I give you this one, H2SO4, if I ionize it, what does it give me? H plus SO4 2 minus 2H plus here to balance the reaction, right? Now BO plus here. Now, if I put calcium here, for example, Ca2 plus, to replace this guy, what salt are we going to form? CaSO4. Is it clear? So that is how we form a salt. Basically, we are saying that the hydrogen ions will be replaced partially or completely. Keep that in mind because there is partial replacement and there is complete replacement. Is that clear? Now I'll show you what partial replacement is. In partial replacement, we form an acid, a salt that is acidic. Is that clear? In partial replacement. Okay? Okay. Now, let's talk about we know it's salt. Now let's talk about the types of salt. Right, types of salt. Then we'll deal with the solubility of salts too. So that here today you'll be able to know how to prepare salt. Okay, if I give you a salt, how do you prepare it? We're going to learn it. Now, is Marvelous's mind here? Are you sure? Do you want to drink water? Okay. You look hungry. Are you sure you're not hungry? Okay. Be sure. You don't know if I can bring bread and sardine out of my pocket. Now let's go. Let's go. Types of salt. Types of salt. Now the first type is what? A normal salt. People don't still know the classification. Yeah. Normal salt, acidic salt, basic salt, what again? Double salt, complex salt. All right, complex salt. Then we talked about hydrated salt. Do you remember?
Yes, sir.
Didn't you talk about hydrated salt? Yeah. When I told you we are doing salt today, you didn't read it. We have an hydrous salt that doesn't have water. Then we have hydrated salt. Is that clear? I mean, this one, all these ones can fall into the category. So this one is not like it's not big thing. Like you might not even write it. I'm trying to show you that I mentioned hydrated so that you know that these ones are different type. They have what is called water crystallization. Let's begin with normal salt. Now, a normal salt is one that is formed. A normal salt is formed when all the replaceable hydrogen ion, have been replaced, the replaceable hydrogen ion of an acid, when all of the replaceable hydrogen ion of an acid replaceable, this is spelling of replaceable hydrogen ion of an acid have been replaced by, please don't have this book, this one is SS2 student. You know, there was something bad I did. SS2 students throughout the term.
So you want to do them like 10 marks for them?
No. They did well in their test and also. I'm in front of you now, you can bring your notes around.
I think that's it.
How is it cheating?
Those people that are not doing
It's not favor, it's I didn't have the time to do all that, don't you know? Ah. Stop lying, please. Yes, you saw it before. You said I treat it. I told you to give him. I should bring it. Let's continue. So when all the replaceable hydrogen of an acid has been what? Replaced. Now, by a metal or ammonium ion. By a metal or ammonium ion. So for example, if we react HCl, thank you, plus NaOH, what do we form here? NaCl. Look, this is how to do it. Isolate the hydrogen and the OH. Okay? Then the remaining Na and Cl. Then you might ask, Master, why do we not write the Cl before the Na? The metal always come before non-metal. Why? Metals are the giver, right? So it's normal to put the givers first before the receivers. Do you understand? All right. So NaCl plus what? H2O. Good. So this is a normal salt. Is that clear? They are neutral to litmus. Is that clear? That's why they are called normal salt. What does that mean? They are neutral to litmus. It will not change their color. Do you understand? Because it's neutral. But there are some normal salts that what's it called now? Change the color of litmus. Yes, and they change the color of litmus. I'll give you the examples, but give me one example in your note of a normal salt, right? A chemical reaction in your note of a normal salt. Produce a normal salt for me. Pick any of the acids we talked about here, and you can react with a metal or a base. Let me see. Correct. But that your base is wrong. Your base is wrong. Correct. No, I've seen. Correct. If you are reacting HNO3 plus CaOH2. We've gone over this before now. The ions will interchange valences, OH minus and Ca2 plus. This one will come here, this one will come here. Is that clear? So they interchange their valences. So we have CaNO3 2. Because NO3 here is what? 1. The valence is what? 1. So it will give this guy 1, and calcium is 2. So it will give this guy 2 plus H2O. Then you can balance it. Maybe I put in 2 here, I think. Is it balanced this way? You put 2 here. Balance your reactions though. Is it clear though? Alright. Now let's there are some normal salts. There are some normal salts that are reactive to litmus. There are some normal salts that are reactive to litmus. These salts are either acidic or basic when dissolved in water. when they dissolve in water, they are normal salts. So in that their normal state, they will be neutral. Exactly. But when you now pour water inside them, they will become what's it called now? Either acidic or basic. Then I ask you a question. Let me test your knowledge on what we have done before. Now this salt is going to react that way. Who can tell me why? This salt is going to react. Will this salt be will it react acidically or basically? Or like how do you what's the adverb for it? Acidically, basically. Like an acid or a base. Is that clear? And you don't know. So this one we really have like a base or an acid. Why?
Because it's not abundant like that.
No. Let me show you what to do here. Remember that what do you notice here? You see that here, the metal is supplied by the base, right? While the non-metal is supplied by the acid. Using that context, tell me again, why would this guy behave like a base?
Because there's not.
If this guy dissolves in water, why will he behave like a base? Let me show you. So you have CO3 2 minus here, right?
Yes.
And Na plus, right? Now, this guy came from where? From an acid, right? Which acid can possibly give us that? H2CO3. What kind of acid is this? Strong or weak? Weak. Which base will give us this? NaOH. Do you understand now? So this is a strong base and a weak acid. Is it making sense now? So this guy, because the acid is weak, it will still have basic property because the base is strong. The base that produced it. They are confused, raise your hand. When you look at a salt, you already know that it has two components, right? There is a cationic component and an anionic component. Na plus and CO3 2 minus in this case, right? Now, look at this salt we formed there. Who supplied the Cl minus? The acid. Exactly. So the anionic component is supplied by the acid. The cationic component is supplied by the base. So, and you know, strong bases are KOH, NaOH, CaOH, LiOH, thank you. But any other one that is not in the first 20 element, like PbOH2, for example, that what a weak base. Do you understand now? Any base that is formed from those guys, that's how to remember it, is that clear? Any base that you see that is not formed from the first 20 elements, it will be what kind of base? A weak base. Do you understand now? But these ones are the strong bases. Is it making sense to you? So I'm now saying that you see a salt, then you look at it, it has cationic and anionic components. Then you say, where is this one going to come from? From an acid. The anionic component always comes from the acid. Then the cationic component always comes from the base, right? Which base will likely produce this? NaOH, right? Which acid will produce this? H2CO3. What kind of acid is this? What kind of a base is this? Do you understand now? So, when a strong base and a weak acid combine, it might still give you a neutral salt, but the neutral salt in solution will behave what? Basic. We have basic property because it's a strong base that gives rise to it. So when you dissolve this thing inside water, what's the test for base? You put red litmus paper into this thing, it will turn into blue, right? So if you put this inside water, you test it with red litmus, it will turn to what? Blue, because it has basic property. But from what you can see here, is it not normal? It's normal because all the replaceable hydrogen ions have been replaced. Does it make sense to you? Are you sure it makes sense? Let me ask you a question. Look at this guy. Now, this one's normal salt. neutral to litmus, in solution or not in solution. Is that clear? But look at this one. What kind of salt will this be? What kind of reaction will you have to litmus? Basic or acidic? Okay, let's see. What kind of cations does he have? Pb2 plus and NO3 minus. What's 2 minus? NO3 minus. So this is the cation, this is the anion. Where does the cation come from? Okay, this cation came from an acid, right? Which acid? This cation came from what? Where does the cation component come from? Yeah, wait. Go and attend to me. Alright, so where does this component come from? And tell me the acid. Okay, that's an acid. Where does the cation component come from? Where does the anion component come from what I just said?
That one. That's the one.
Which second one? Anion or cation?
Anion.
The anion. It comes from an acid. Which acid? What's okay? Was it not all of you explained to together? I mean, have you not been writing these reactions for long? Who supplies the anion component? The acid. This one said acid supplies this. When you said acid is a substance that dissolves in water to produce hydrogen ion as the only positive ion, and there's a positive ion here. So lead and hydrogen will be positive now. Is that not what he's saying? He's talking like drunk people. So that is what? That lead is from what? From base. So which base do you suspect? Which base? Tell me the base. PbOH. Do we not know base? Do we not know acid? Okay. Is it clear? So I said that the base is metallic oxide or metallic hydroxide. We've mentioned that before. Is that clear? So to know the base that supplied it, just put your metal and hydroxide. Is that clear? I mean, of course, you may not say, Master, but an oxide can also give you that. But we already said reactions are carried out in water. So in solution, this is what we have. Do you understand now? When dissolved in water. Do you understand? Even though not all, most oxides are insoluble, we'll soon get to that. But the idea is that's how to just picture it. Is that clear? So now, this is the base that supplies this, right? And this is the acid that will supply the anionic component. Is it clear? So what kind of acid is this? What kind of base is this? So this salt will have which property? Acidic property. Because it's from a strong acid and a weak. Is it clear? Let me give you one more. Look at this guy. What kind of property will this one have? Acidic or basic property? Acidic. What about you? Basic. What about you? Basic. Let's analyze it. Pb2 plus and Cl minus. Which components? Who will supply this, an acid or a base? Who will supply this, an acid or a base? So which acid do you suspect will provide this? HCl. Strong acid or weak base? Or strong base? Strong acid or weak acid rather? Strong acid. Which base do you suspect to supply this? PbOH 2. Okay, so basic, right?
No.
What kind of base is it, strong or weak?
Weak.
What kind of acid is it, strong or weak?
Sugar.
So what property does this guy have?
Acidic.
Acidic. Is it right? I know you've got it. Don't be forming. See, I don't know why some people are not thinking. Just leave the people that are not thinking. Then let's both of us be communicating, exactly. And partially you. What's funny? Have you not been taught in class before? I think I've not experienced something like this in his presence. I've not experienced in your presence. Upstairs. We caught him, right? See his shoe. Should we continue? Is it clear? Don't lie, is it clear? Of course, we'll still do more examples. Is it clear? Look at this one. Mm. Oh, what am I right? No. What kind of property will you have? Acidic or basic property? Basic property. Okay. Let's see. SN2 plus. This thing, right? Carbonate. This one will come from weak acid stressful. This one will come from. Now it's actually a weak base, but its weakness is stronger than the strength of this one. Do you understand now? That's why this one will still be basic. Exactly. But the idea is this. The idea is this. If they are both weak, it's normal salt. It's normal salt. It should be neutral. No, all the salts you have been using, they are normal. They are normal. But in solution, they will display those properties. Exactly. Do you understand what I'm saying? Let me use one that is commonly asked. This salt, what property will it display? Acidic or basic? Acidic. Is it clear now? Is it hard? Where were we, please? Now, so it's clear now, right? So we are good with normal salt. Normal salts, they are neither acidic nor basic, but in solution, depending on their source. Is that clear? Put it down. Normal salts, depending on their origin, normal salts, depending on their origin, may display acidic property or basic property in solution. May display what? Acidic or basic property in solution. Full stop. Or basic properties in solution. So your assignment is go home and write 5 normal salts that are acidic, that have acidic property, 5 normal salts that have basic property. Differently, is that clear? 5 normal salts that have acidic property, 5 normal salts that have basic property. Is it clear? All right. Now, one of what you will do is this. You will state reason why each one is acidic. Do you understand? Do you understand? Because I want you to state the origin of the. For example, look at this. What kind of salt will this be? Acid, what kind of property will it have? Acidic or basic?
Basic. No, acidic.
Normal. Strong acid, strong base. Is it clear? Is it clear? All right. Now let's go to the second one, acidic salt. Do you understand the assignment? When you write a salt, you write you bring the components, the origin, exactly the equations that probably produced it. So you now write weak acid, strong base, strong acid, weak base, whichever way. Is that clear? Right. So now let's go to acidic salt. An acidic salt is a salt that is produced when the replaceable hydrogen ions in an acid, when the replaceable hydrogen ions in acid are only partially replaced, when the replaceable hydrogen ions in acid are only partially replaced in an when the replaceable hydrogen ions in an acid are only partially replaced by metals or ammonium ion, by metals or ammonium ion. Now, so when some, not all, only some of the replaceable hydrogen ion have been replaced in an acid, then we form what? An acidic salt. Why? Because there will still be a proton inside. So that guy is a salt, but it's not a normal salt. Why? Because it still has hydrogen. Is it making sense? Example is this. Let us react H2SO4 with NaOH, for example. What will happen? You see that in this case, there is a limited supply of OH, right? Or think of it as limited supply of the metal, 1 is that clear? Limited supply of the metal, but bountiful supply of protons, right? So you have what? NaHSO4. We did this before now. Do you understand? NaHSO4. Do you notice that there's still a proton there? Do you understand now? There's still a proton because the protons they have not been totally replaced by sodium. Is it clear? So this will give us this plus water. I mean, if you now supply sodium in excess, sodium hydroxide in excess, it will now neutralize it totally. Is that clear? But in this state, this is sodium hydrogen tetraoxophase 6. Is that clear? In this state here, there's there's little supply of the metal, but more this thing, proton is supplied in excess. Do you understand? So then you still have proton inside. Is it making sense? Is it clear to you? Are you sure? Another one. Give me, what about if we have this H3PO4 reacting with maybe MgOH2. You notice this guy is supplied limited supply, right? Give me one by yourself. Give me a reaction on your own. Pick a base of your choice and pick an acid that can supply proton in excess. Come, look here. You know that if you pick HClA, it doesn't work. Yes, all right. Give me. ZMH2 Mg2H. Who's done? Let me see. I know that reaction is wrong. That one is correct. Correct. Name the salt. Well, just say the name of your acidic salt. Potassium hydrogen. Do you understand? I think I remember one song with my student. Sodium hydrogen tetraoxosulfate 6. Sodium. So that one will be potassium hydrogen tetraoxosulfate 6. Is it clear? Alright, let's go to the next one. Basic salt. This is a salt. This part should not be problems for you because we've gone over this before. And so make sure you read your notes again. Is that clear? Is it clear to you? See, this reaction is actually wrong. Do you understand? And but the search you did is actually correct. Do you understand? Hypothetically speaking, that is correct. But your base, correct the base. His base is wrong. Help him to correct the base. Now look at this. A basic salt is when we get a basic salt when we supply hydroxide in excess. When we supply what? Hydroxide in excess. So for example, I react, but then there is limited supply of the proton. Do you understand? So for example, we react, give me a base that is suitable for this, that has hydroxide supplied in excess. Exactly. Or zinc OH2. That was one, this was what came to my mind. Thank you. So if you supply both, if you supply this, you see it's obvious that OH is supplied in excess here compared to the hydrogen here. See, hydrogen is one here. Makes sense? That's just how to come about it. So this gives us what? Zinc, OH is still there, right? Then Cl. Then what would this one be? CaOH, Exactly. So this one have what? Zinc hydroxide chloride, calcium hydroxide chloride. All right. Let's move quickly. Double salt. We've talked about double salts before. The double salt. This is formed when two normal salts are mixed. This is formed when two normal salts are mixed. The resulting double salt, full stop. Full stop. Then the resulting double salt has a property which is different. Has a property which is different from the individual normal salts. Is it clear? All right. So double salt. Now complex salt. We talked about some examples here. This alum guy, that's my classical example. Do you remember? K2SO4 Al2 SO4 3 dot 12H2O. Exactly. But this is a double salt, right? There are two salts there. Look at it. Is it clear? Sometimes you might see it written like this. I don't know, I think this way it is written for this one. I think they normally write it this way too. K2. Let's leave it. That's a double salt. Exactly. Alright. Another one is complex salt. A complex salt is one which contains complex ions. A complex salt is one which contains what? Complex ions. So, an example of a complex salt is this. We've not done coordinate covalent bond, right? But we've done Vesper theory. So you should be able to tell me the shape of this thing, in fact. But this one is formed from coordinate covalent, the complex side of this thing. Exactly. This guy will be K4FeCN6, for example. When this guy ionizes in water, watch. This is why we call it complex salt. When this guy ionizes in water, it will form K plus, that will be 4K plus, right? Plus FeC, no, FeCN6 4 plus and 4 minus, sorry, 4 minus. Does it make sense? Do you understand now? So this is the idea of a complex salt. So this is the complex ion here. This is called what? Complex ion. Another one is if we have the same K for Fe, it's okay for K2 now. You could use any first guy or any of the that guy. And with ammonia, NH3, I think it's also 6. The charge here will be, what will be the charge? What this means is iron is in the middle. What will be the hybridization? This one will be 1, 2, 3, 4, 5, 6. Do you remember this? So what will be the hybridization? This will be sp3d2. Have we forgotten? Because around Fe, how many things are arranged? 1, 2, 3, 4, 5, 6. So one will be in this P 1, 2, 3, 4, 5, 6. Is it clear? What's the hybridization of CH4? Of the C in CH4? What will be the hybridization? sp3. Is it clear? He doesn't remember anything about it. That day you were playing with the guy in front of you, what's it? Fadia. So how do you remember? You remember, yeah? What's the hybridization of? Look at this guy. These two carbons. What's the hybridization of this carbon? sp2, Baba. 1, 2, 3 things. Go and review your notes. On Vesper theory. You wrote notes, didn't you? Go and review your notes. Here's my point. That ammonia, we are going to have 6 bonds around it, and we have ammonia here, NH3 here, NH3 here, NH3 here, NH3, NH3. Now, normally in ammonia, the Lewis diagram of ammonia looks like this, right? And around nitrogen, we have 1, 2, 3, 4, 5. Am I correct? This is the Lewis diagram, right? The nitrogen dot. So 3 hydrogens will now connect. One will connect here, the other will connect here, the other will connect here. Make sense? What will be the shape of the molecule? Do you remember? Okay. Don't go and read your notes. Baba did what again, please? I wanted to show you this now. Watch. Where were we, please? Where was I? Yeah, I want to show you this, right? This is the molecule, right? So this guy has formed bond. So how many non-bonding electrons do we have? 2. 2 non-bonding electrons. So the 2 non-bonding electrons here, being a coordinate covalent, the 2 will be supplied here. But what's the valency of iron? It has 2 valencies. 2 plus 2 and plus 3. Okay. I'm trying to look for the charge here. I can't remember. It's the charge here that will help us to know the number here. Do you understand what I'm trying to do? I think it's +3. Do your research. Is that a chemistry textbook? Okay, copper is used there. Copper is used there. Let's use that of copper. It's still ammonia around it, right? See, for copper, it will be 2 plus. Since iron is 2 plus or 3 plus, iron is +3 or plus 2 or +3, right? And so for the one of copper, it was 2 plus, right? So this one, I think it will be 2 plus or 3 plus. Let's use 2. So 2 here. So the idea is that this guy here is a complex. Do you understand? Is a complex ion. So that's this is a complex salt. This is also a complex salt. Is it clear? Let's go to anhydrous salt. Anhydrous salt are salt. Have you seen the examples? I read the examples. But please verify this for me. Verify this guy for me. The charge on this one. If this guy ionizes, so that I will know the number that will be here. We are assuming 2 now because I saw 2 for copper. What will be the realization of that copper there? What will be the look at the complex salt of copper. So for example, if this guy reacts with potassium to be K2 Cu, if he reacts with K plus, for example, it will give us what? K2 Cu what? NH3 4. Is it clear? So is it clear? If you react it with aluminium, 3, there will be 3 here. Is that clear? And 2 for aluminium. You understand that thing, right? Alright. It's own comment. Okay. Your own assignment, write other complex salts. 5 more. You can use the complex ions we have used. Is that clear? Complex ions. One thing with these complex ions is they form with what we call ligands. Ligands or ligands. I think it's ligand, that's the pronunciation. But you know, this chemistry class. But I think it's ligand. But it's spelled like ligand. So ligands are these guys. Those metals. Is that clear? Those metals in the transition series, human transition series. So those guys, they are the ones that this guy normally form complexes with. The complex ions are usually formed, the most common ones you will see are usually formed with ammonia and cyanate. Is that clear? Cyanate. This is cyanate, right? And this is, what's this? He's a radical. What's the guy? Is he ammonia or ammonium?
Ammonia.
Which one is that ammonium? NH4. NH4 plus. It's an ion. This is ammonia. Exactly. Anyways, let's go. Anhydrous salts are salts that do not contain water of crystallization. Anhydrous salts are salts that do not contain water of crystallization. Look at it. And anhydrous salts are salts that do not contain water of crystallization. Water of crystallization. This crystallization. Crystallization. Z. Where? Yeah? Crystallization. That would be like. No, crystallization is Z for everyone, whether it's British or American. Exactly. It's words like organization and all. Like you have British American spelling. Is it clear? Alright. So that's water of crystallization now. So anhydrous, what does the word an mean? And what does the word hydro mean? Hydro mean ah. What does hydro mean? You're trying to remember what? Stand. What does hydro mean? Yes, it's water. He said he's trying to remember. Are you okay? What does oxy mean?
Oxygen.
What does the oxy there? What does it mean? What does oxy mean? Yeah. And hydro us. What is aerobic? Using oxygen. God bless you. Now, what is anaerobic? Does not use. So, what does that an mean? Not. An means what? Not. What does hydro mean? Water. Is it now clear? So they don't have water or crystallization. Is it clear? When we get to oxygen in non-metals, we'll discuss types of oxides. We have anhydrides, acid anhydrides. Those are acidic oxides. So what does an mean? Not. Hydride from hydro. Hydro means what? Water. Oxy means acid. Oxy means what? What does gene mean? Hydrogen. What does the gene there mean? Sit. And you read it, or didn't you? You read it, or didn't you? Or who did not read about oxygen or hydrogen here? Apart from me, who has not read? By the way, they haven't sent it to you to read those topics. Pause that thing. So anytime I did not come,